And let's show that. To show, and to talk about independence, we need the concept of conditional probability. Let's use this example again. Let us say that we know B is happening. So we know we're in this piece here. Okay? Is it possible for A to happen? Yes. It's possible for A to happen if we land there. And remember, the point of a Venn diagram is so that the areas, the ratio of the areas represent probability. In a sense, since we know B has happened, we have shrunk the state space so that it's just B, right? And by the same logic, the probability that A now happens is the ratio of what to what? Probability of?
Probability of A and B over B.
Exactly. And that is defined to be the probability of A given that you know B has already happened. So that animal right there, this vertical line, is read given. And the order is crucial here. So, see, A given B, the second is given, the second is known with certainty. It's already happened. What is then the probability that A happens? That's what this is. So it doesn't make any sense to compare probability of A given B with something like the probability of B happening. You can only compare this to the probability of A happening or the probability of A happening conditional on something else. So we're going to use this definition quite a bit. And specifically, here, we're applying the definition, and we find the probability that Collins is profitable, given that Markley is profitable, is 51%. Does anyone remember what the unconditional probability that Collins was profitable was?
80%.
No, it was 48%. Got an 8 in it. So, my question to you is, does knowledge about Markley tell us something about the profitability of Collins? Yes. Not with certainty, but it tells us something. Yes? And that something is a result of the subjective probabilities. It lies in the structure of that probability distribution. Now, if you go back one, you multiply across by P of M and substitute A and B, you get this. Right? If we just divide by P of B, we get the same definition. Probability of A given B is the joint probability divided by P of B. But multiply across and you get what's called the multiplication law. And that's actually sometimes very useful as well. This is just to show you that what we get is consistent. If you recall from before, the probability of both Markley and Collins being profitable is 36%. When you calculate using these numbers, you get the same thing. The point of that is there's an immense amount of redundancy in this. You basically can find 3 or 4 ways of doing the same thing for almost anything. Okay, now we get to the real meat, independence. If, in fact, B tells you nothing about A, then knowledge of B doesn't change the probability of A. Therefore, the probability of A is unchanged. This is true. Now, that can't be true if knowledge of B does anything at all about A. So, for instance, if you have mutually exclusive events, if A and B are mutually exclusive, the probability of A given B is mutually exclusive.
Probability of either minus, like, You asked for the probability of A.
No, what I asked was, if you have A and B are mutually exclusive like this,
Right.
then if B has happened,
Zero.
it can't happen. So the probability of A given B is 0. Yes? It can't happen. Alright, so by definition, if you have mutually exclusive events, you do not have independence. Because independence requires that this equality holds. And this equality, or rather the concept of independence, lets us do several things. One, it lets us actually do statistics. If you didn't have independence, specifically independent draws for a sample, you couldn't calculate the probability of seeing particular samples. And that's what lies under all of inferential statistics. So independence is really critical to everything we're going to do from here on out.